Imagine a time long before the whisper of wind through trees, before the rhythmic crash of waves on a sandy shore, before even the simplest single-celled organism drifted in ancient waters. Picture a world utterly alien to our own, a realm of molten rock and furious storms, yet holding within its very fabric the silent promise of everything that was to come. How did life, with its intricate dance of replication, metabolism, and adaptation, emerge from the inert dust of the cosmos? How did the inanimate learn to live? This is perhaps the most profound question we can ask, a mystery woven into the very fabric of our existence. To begin unraveling this grand tapestry, we must journey back, not just billions of years in Earth's history, but even further, into the depths of space and time. Our story doesn't start on Earth itself, but in the heart of distant, dying stars. These colossal celestial furnaces, many times the size of our own sun, spent eons fusing lighter elements into heavier ones, hydrogen into helium, then helium into carbon, oxygen, nitrogen, and ultimately iron. When these grand stars finally reached the end of their lives, they exploded in spectacular supernovae, scattering their enriched guts across the nascent galaxy. This cosmic shrapnel, laden with the fundamental building blocks of planets and eventually life, drifted through the interstellar medium, waiting for its next act. Our own solar system, including the Earth, was born from one such cloud of stardust and gas, roughly 4.6 billion years ago. Gravity, the invisible sculptor of the cosmos, pulled this diffuse material together, forming a swirling disk. In the center, our sun ignited, and further out, countless smaller clumps coalesced, growing steadily through repeated collisions. This was the process of planetary accretion, a violent and chaotic ballet of rock and ice. Our early Earth was a hot, turbulent world, constantly bombarded by asteroids and comets, remnants of the solar system's formation. Its surface was a searing ocean of magma, glowing with incandescent heat, releasing vast quantities of gases into a nascent atmosphere. This Hadean eon, spanning from Earth's formation about 4.5 billion years ago to roughly 4 billion years ago, was a time of unimaginable intensity. The skies would have been perpetually dark, not from clouds, but from thick volcanic plumes and dust kicked up by impacts, punctuated by streaks of lightning that would make even the most violent modern storms seem like gentle breezes. The atmosphere itself was a stark contrast to the breathable air we enjoy today. It was a reducing atmosphere, meaning it lacked free oxygen. Instead, it was rich in carbon dioxide, nitrogen, water vapor, methane, and ammonia, along with various sulfur compounds. This chemical cocktail, while toxic to most modern life, was absolutely crucial for the earliest steps towards life. But how did this scorching volcanic world begin to cool enough for water to condense, for oceans to form? Over millions of years, as the bombardment lessened and Earth radiated heat into space, the molten surface began to solidify, forming a primitive crust. As temperatures dropped below 100 degrees Celsius, 212 degrees Fahrenheit, the immense amounts of water vapor in the atmosphere, released by volcanoes and delivered by icy comets, condensed and rained down, perhaps for thousands of years. These torrential rains filled basins and depressions, creating the Earth's first oceans, vast, warm, and rich with dissolved minerals. These primordial oceans would become the cradle for life, but they were still far from teeming with organisms. They were, instead, a vast chemical laboratory. It is within this primordial setting that the first truly critical step occurred. the formation of basic organic molecules. These are carbon-based compounds, distinct from the inorganic minerals and gases that dominated the early Earth. Think of them as the fundamental Lego bricks of life. Two particularly important classes are amino acids, the building blocks of proteins, and nucleotides, the building blocks of DNA and RNA. How did these complex molecules arise from simple inorganic precursors? Scientists have explored several compelling hypotheses. One of the most famous and foundational experiments in this field was conducted in 1952 by Stanley Miller and Harold Urey. They constructed a sealed apparatus designed to simulate the early Earth's conditions. A flask of boiling water represented the ocean, providing water vapor. Another flask contained a mixture of methane, ammonia, and hydrogen, representing the early atmosphere. Electrodes generated electrical sparks to simulate lightning, and a condenser cooled the gases, allowing water to rain back into the ocean. After just 1 week, Miller analyzed the contents of his ocean and found a startling array of organic molecules, including several types of amino acids. This groundbreaking experiment demonstrated that the basic building blocks of life could spontaneously form under plausible early Earth conditions, given the right energy sources like lightning. While the exact composition of the early Earth's atmosphere is still debated, some models suggest it was less reducing than Miller and Urey assumed. Subsequent experiments using different gas mixtures, including those rich in carbon dioxide and nitrogen, have still successfully produced organic molecules, albeit sometimes in smaller quantities or different arrays. This suggests that even if the atmospheric recipe was slightly different, the kitchen was still open for business. Beyond the atmosphere, other powerful engines could have driven the creation of these molecules. Imagine the deep ocean floor, where tectonic plates pull apart, allowing superheated mineral-rich water to gush from cracks in the crust. These are hydrothermal vents, often called black smokers or white smokers, due to the plumes of dissolved minerals they release. The extreme temperature gradients, from near-freezing deep seawater to hundreds of degrees Celsius at the vent openings, coupled with a wealth of dissolved metals and gases like hydrogen sulfide, create powerful chemical disequilibria. This energy, rather than lightning or UV radiation, could have fueled the synthesis of organic molecules. Some scientists hypothesize that the porous, mineral-rich structures around these vents could have acted as microscopic reaction chambers, concentrating molecules and providing catalytic surfaces for more complex chemistry to unfold. Yet another source for life's initial ingredients might have arrived from beyond Earth itself. The early solar system was a violent place, and Earth was continuously pelted by meteorites and comets. Crucially, many of these extraterrestrial visitors, particularly a type known as carbonaceous chondrites, are rich in organic compounds. For instance, the Murchison meteorite, which fell in Australia in 1969, was found to contain over 90 different amino acids, some of which are common in terrestrial life and others that are not. It also contained nucleobases, the fundamental components of DNA and RNA, as well as sugars and fatty acids. This incredible discovery provided direct evidence that the universe itself readily produces these essential organic building blocks. So, did life's ingredients form here on Earth? Or were they delivered from space? Or perhaps a combination of both? The scientific consensus leans towards a mix, with both endogenous, Earth-based, and exogenous, space-based, processes contributing to the chemical richness of the early planet, regardless of their precise origin, whether forged in the electric crackle of the early atmosphere brewed in the deep-sea vents, or delivered from the cold vacuum of space. These fundamental organic molecules began to accumulate. They didn't just float aimlessly. They collected in specific environments, forming what scientists colloquially refer to as the primordial soup. This wasn't necessarily a planet-wide ocean of thick, viscous goo. Instead, it likely refers to localized concentrations, warm, shallow tidal pools, sheltered lagoons, or even pores within rocks near hydrothermal vents. Why did these molecules concentrate? In shallow pools, repeated cycles of evaporation and rehydration could have significantly increased their density. On mineral surfaces, like clays, organic molecules can stick and accumulate, providing a localized environment where they are not simply diluted into the vastness of the ocean. These clay minerals are particularly intriguing, as their layered structures and charged surfaces can attract and organize organic molecules, potentially acting as templates for more complex assemblies. Crucially, in this early Earth, there was no life as we know it to consume or break down these newly formed organic molecules. Without bacteria, fungi, or other organisms to metabolize them, these compounds could persist and accumulate over vast stretches of time, reaching concentrations that would be impossible today. This allowed the chemical laboratory of early Earth to simmer, undisturbed, for millions of years. The primordial soup, then, was not just a collection of ingredients. It was a dynamic, chemically active environment, constantly being stirred by geological forces, energized by lightning and solar radiation, and replenished by both terrestrial synthesis and cosmic deliveries. This stage, the formation and accumulation of the fundamental organic building blocks, represents the absolute bedrock of abiogenesis, the process by which life arises from non-living matter. It's the moment when the universe, having forged the elements in stars and assembled a planet, began to lay out the very first pieces of the puzzle. The stage was set, the ingredients were present, and the conditions were ripe for the next, even more astonishing transformation. The assembly of these simple bricks into something far more complex, something that could begin to resemble the very first stirrings of life. What forces would then compel these simple molecules to link together, to form longer, more intricate chains, moving beyond a mere soup of ingredients towards the first fragile structures of living systems? Imagine a world where the very ground beneath your feet was not just inert rock, but a vibrant chemical crucible, humming with the potential for life. How could the scattered dust of the cosmos, having coalesced into simple molecules, then assemble itself into the intricate blueprints and machinery of living beings? This fundamental shift, from individual chemical ingredients to long, complex chains, marks a crucial step in life's grand emergence. In the previous moments of our journey, we explored how the early Earth, a turbulent and dynamic planet, managed to forge or collect the essential building blocks of life: amino acids, the constituents of proteins, and nucleotides, the units that form nucleic acids like DNA and RNA. These small, relatively simple organic molecules, perhaps concentrated in what scientists call the primordial soup, filled the ancient oceans or collected in smaller, shallower pools. But having the ingredients is only half the story. Think of it like having all the individual bricks, timber, and glass panes for a house scattered across a vast field. How do these pieces spontaneously come together to form a structure? The challenge of assembling these simple molecules into the long, complex chains known as polymers was immense. One of the greatest hurdles was the sheer dilution of the primordial soup. Imagine trying to find a specific grain of sand on an immense beach, let alone trying to get two particular grains to stick together, and then a third, and a fourth, in a precise sequence. In a vast ocean, even if there were billions of amino acids or nucleotides, the chances of two specific ones encountering each other, reacting, and forming a stable bond, then repeating this process many times over, were incredibly slim. The molecules were simply too spread out, like individual swimmers lost in an endless sea, rarely bumping into each other with enough force and in the right orientation to perform a chemical handshake. How could nature overcome such a fundamental problem of scale and chance? Furthermore, the process of linking these small organic molecules together, known as polymerization, often involves a chemical reaction called dehydration synthesis. This means that to form a bond between two molecules, a molecule of water must be removed. In a watery environment like an ocean, this is thermodynamically unfavorable. It's like trying to dry something out while it's submerged in water. The environment naturally pushes the reaction in the opposite direction, toward breaking things apart through hydrolysis, which adds water. So, not only did the molecules need to find each other, but they also needed a source of energy and a way to overcome the pervasive presence of water, which actively sought to undo any newly formed bonds. Where would such a potent, consistent force come from, capable of defying the very nature of an aqueous environment? Scientists have proposed several ingenious solutions to this polymerization puzzle, each leveraging the unique conditions of the early Earth. One compelling scenario unfolds in the dynamic environment of portidal pools, or shallow ponds. Imagine a warm, rocky coastline, perhaps on a volcanic island, where shallow depressions in the rock fill with seawater at high tide. As the tide recedes and the sun beats down, the water in these pools would slowly evaporate. With each passing hour, the volume of water would decrease, but the number of dissolved organic molecules would remain the same, leading to a dramatic increase in their concentration. As the water level dropped, the once dilute soup would become a thick, viscous broth, a far cry from the vastness of the open ocean. Molecules, now packed closely together, would collide much more frequently. The energy from the sun, absorbed by the increasingly concentrated mixture, could help drive the dehydration reactions, overcoming the thermodynamic barrier. This wasn't a one-time event. These pools would undergo cycles of wetting and drying, filled by the tide or rain, then slowly evaporated by the sun. Each cycle would offer a fresh opportunity for molecules to concentrate and react, building longer chains with every iteration. Think of it like a natural, slow-motion evaporation experiment, performed daily over millions of years. Could these rhythmic environmental changes have been the persistent sculptor of early life's fundamental architecture? Such environments also offered surfaces where molecules could bind, further increasing their local concentration and providing a scaffold for reactions. For example, some experiments simulating these wet-dry cycles have shown that simple amino acids can link together to form short protein-like chains, called peptides, and nucleotides can form short RNA-like strands. The repeated heating and cooling, wetting and drying acted as a natural chemical pump, gradually nudging these simple building blocks towards greater complexity. Another powerful mechanism for overcoming the dilution problem involves catalytic surfaces of clay minerals. Picture the fine, silty sediments accumulating at the bottom of these shallow pools, or even on the shores of the primordial ocean. Many clay minerals, such as montmorillonite, possess a unique layered structure and electrically charged surfaces. These surfaces act like tiny molecular magnets, attracting and binding organic molecules from the surrounding water. Once adsorbed onto the clay surface, The molecules are no longer diffusing randomly in the vastness of the water. They are held in close proximity, effectively concentrated by orders of magnitude. More than just concentrating molecules, these clay surfaces can also act as catalysts, guiding and accelerating chemical reactions without being consumed themselves. The charged nature of the clay could orient the amino acids or nucleotides in a way that favors the formation of specific bonds, making the polymerization process more efficient and selective. Think of the clay surface as a molecular workbench, holding the small building blocks firmly in place and presenting them to each other in the perfect alignment for joining. This not only speeds up the reaction, but also helps ensure that the correct types of bonds are formed. Furthermore, the layers of clay could offer protection to the nascent polymers, shielding them from damaging ultraviolet radiation, which was much more intense on the early Earth due to the lack of an ozone layer, and also protecting them from degradation by hydrolysis. How remarkable is it that seemingly inert dirt could have played such an active, sophisticated role in the genesis of life? While the warm, sunlit surface environments offer compelling scenarios, another powerful contender emerges from the deep, dark abyss: hydrothermal vents. Unlike the shallow pools, these underwater geysers are located far beneath the surface, where superheated, mineral-rich water spews from cracks in the Earth's crust. There are primarily two types of vents considered: the extremely hot black smokers, which can reach temperatures over 400 degrees Celsius, 750 degrees Fahrenheit, and the cooler, more sustained, alkaline hydrothermal vents. While black smokers offer immense energy, their extreme temperatures might be too harsh for fragile organic molecules to persist and polymerize. Alkaline vents, however, present a particularly attractive environment. These vents form where seawater reacts with rocks deep within the Earth's crust, producing alkaline, hydrogen-rich fluids that seep out at relatively mild temperatures, typically between 40 and 90 degrees Celsius, 100 to 190 degrees Fahrenheit. As this alkaline fluid mixes with the slightly acidic, carbon dioxide-rich primordial ocean water, it creates natural chemical and temperature gradients across the porous mineral structures of the vent chimneys. These gradients act like a primitive electrochemical battery, providing a continuous source of energy for chemical reactions. The microscopic pores within the vent structures could trap and concentrate organic molecules, preventing them from drifting away into the vast ocean. Here, protected from destructive UV radiation and meteorite impacts that plague the surface, molecules could slowly but steadily react. The continuous flow of chemical energy from the vent system could drive polymerization, much like a constant gentle push, encouraging small pieces to knit together into larger wholes. Could the quiet, hidden depths of the ocean have been the true cradle of creation? So, whether it was the rhythmic drying and wetting of sun-drenched tidal pools, the catalytic embrace of clay minerals, or the sustained chemical energy of deep-sea hydrothermal vents, the early Earth offered diverse environments where simple organic molecules could overcome the challenges of dilution and thermodynamics. Each of these scenarios is supported by laboratory experiments that have successfully demonstrated the formation of short protein-like chains, peptides, and RNA-like strands, oligonucleotides, under simulated early Earth conditions. Scientists continue to debate which environment or combination of environments was most crucial, but the fundamental principle remains. The environment itself provided the mechanisms to knit scattered parts into structured chains. The products of this polymerization were revolutionary: proteins and nucleic acids. Proteins, formed from sequences of amino acids, are the workhorses of modern cells, performing countless functions from structural support to catalyzing chemical reactions. Even simple short protein-like chains could have begun to exhibit rudimentary catalytic abilities, speeding up other chemical reactions in their environment. Nucleic acids, formed from sequences of nucleotides, carry genetic information. While modern life relies heavily on DNA, many scientists believe that RNA, a simpler form of nucleic acid, played a more central role in the very early stages of life. What extraordinary potential was locked within these newly formed chains? These newly formed polymers were still far from fully functional biological molecules, but their emergence marked a profound leap in complexity. Yet, even as these chains began to form, new puzzles arose. For instance, why does all known life on Earth exclusively use left-handed amino acids and right-handed sugars? This phenomenon, known as chirality, is a deep mystery. Many organic molecules exist in two mirror image forms, like a left and a right hand, while chemical synthesis usually produces an equal mix of both. Life selected only one. Was this selection a random chance event in a localized environment? Or was there a subtle preference imparted by mineral surfaces, or perhaps even by circularly polarized light from distant stars? Furthermore, these early polymers, even if they formed, were still relatively fragile. How did they persist long enough in these dynamic, often harsh environments to become useful? The same environments that promoted their formation might also have led to their degradation. This suggests that the processes of formation and protection had to be finely balanced, perhaps within microenvironments where conditions were just right, allowing these early molecules to accumulate and evolve without being immediately broken down. The quest to fully understand the polymerization puzzle continues to be a vibrant area of scientific research. Laboratories around the world are recreating early Earth conditions, testing various minerals, temperature gradients, and chemical mixtures to observe how these crucial building blocks came together. Missions to comets and asteroids, such as NASA's OSIRIS-REx, are bringing back samples that can be analyzed for complex organic molecules, offering clues about extraterrestrial contributions to Earth's primordial soup. The ongoing debate about whether life began in warm little ponds, deep-sea vents, or perhaps even originated in space and hitched a ride on meteorites, only underscores the complexity and richness of this scientific inquiry. Each hypothesis provides valuable insights into the fundamental processes that must have occurred. Ultimately, the linking of simple molecules into these longer, more intricate chains was an indispensable step. It transformed a mere collection of ingredients into rudimentary blueprints and tools, setting the stage for the next, even more astonishing development: the ability of these molecules to make copies of themselves. From scattered parts, the early Earth had engineered the very first, albeit crude, forms of molecular machinery. But how could these complex chains begin to replicate themselves, thereby initiating the grand dance of evolution and truly blurring the line between inanimate matter and living systems? Imagine a world, billions of years ago, where the very concept of life was yet to be born. A world of swirling chemicals, warm waters, and volcanic gases. We've explored how simple building blocks, the molecular Lego bricks of existence, could have formed and gathered in this ancient landscape. But how did these inert molecules, these tiny pieces of matter, begin to do anything? How did they start to organize, to replicate, to become more than just a random collection of atoms? In every living cell we know today, there is a fundamental partnership at play. DNA, a magnificent spiral staircase of information, holds the blueprints for everything the cell needs, the complete instruction manual for building and operating an organism. And proteins, the tireless workers and complex machines, carry out almost all the cell's functions, building structures, catalyzing reactions and processing energy. They are the hands, tools, and motors of the cell. But here lies a profound mystery, a cosmic chicken or egg dilemma that perplexed scientists for decades. DNA needs proteins to replicate itself and to express its information, and proteins are built according to instructions encoded in DNA. So which came first in the very first living system? How could one exist without the other? For a long time, this question seemed to present an insurmountable hurdle to understanding life's origins, a circular problem with no apparent starting point. But then, a brilliant and elegant hypothesis emerged from the scientific community: the RNA world. This idea suggests that there was a time, long before DNA became the stable archive of genetic information, and before complex proteins became the master catalysts, when a different molecule held center stage. This versatile molecule was capable of performing both roles, storing genetic instructions and catalyzing the chemical reactions necessary for its own existence and replication. That molecule is RNA, ribonucleic acid. To truly appreciate the genius of the RNA world, let's take a closer look at RNA itself. Imagine DNA as a robust, double-stranded ladder, perfectly designed for stable, long-term information storage, carefully protected within the cell's nucleus. RNA, in contrast, is typically a single-stranded molecule. While it shares many structural similarities with DNA, both are polymers made of repeating units called nucleotides. Its single-stranded nature allows it to be much more flexible. Unlike the rigid double helix of DNA, RNA can fold into incredibly intricate, complex three-dimensional shapes, much like a piece of paper that can be crumpled, folded, and sculpted into a functional object. These complex folds are crucial, as they enable RNA to act not just as a passive message carrier, but as an active participant in chemical reactions. Each RNA nucleotide consists of three parts: a sugar molecule called ribose, a phosphate group, and one of four nitrogenous bases: adenine A, guanine G, cytosine C, or uracil U. Notice the subtle but significant difference from DNA, which uses deoxyribose sugar and thymine T instead of uracil. The ribose sugar in RNA contains an extra oxygen atom compared to deoxyribose, a seemingly minor detail that actually makes RNA chemically less stable and more reactive than DNA. Yet, this very instability, far from being a flaw, might have been key to its early evolutionary role, allowing for more rapid change and adaptation. In modern cells, RNA plays many vital roles. Messenger RNA carries genetic instructions from DNA to the protein-making machinery. Transfer RNA helps assemble proteins by delivering the correct amino acids. And ribosomal RNA forms the core structure of ribosomes, the molecular factories that build proteins. Its enduring presence in these fundamental ancient processes, even today, hints at its deep historical importance. But the true revelation, the one that unlocked the door to the RNA world hypothesis, came with a groundbreaking discovery in the early 1980s. Scientists Sidney Altman and Thomas Seck independently discovered that certain RNA molecules could, surprisingly, act as enzymes. These catalytic RNA molecules were named ribozymes. For decades, it was a fundamental dogma of biochemistry that only proteins with their vast array of 20 different amino acid building blocks and complex folding capabilities could perform the intricate work of speeding up biochemical reactions. The discovery of ribozymes was like finding out that the scroll holding the blueprint could also somehow assemble the house, or that the musical score could play itself. This was a paradigm shift. It showed that RNA wasn't just a passive intermediary. It had the potential to be a dynamic, active player in the chemical drama of early life. Imagine a primitive system, not yet equipped with the sophisticated protein enzymes we see today, but instead relying on these simpler, yet potent RNA catalysts. What if these RNA molecules could not only store information about their own sequence, but also facilitate the very reactions needed to replicate themselves? This is the core elegance of the RNA world hypothesis. It neatly solves the chicken or egg dilemma by proposing a single molecule that could do both, serving as both blueprint and builder. So, if RNA could both store information and catalyze reactions, how might the first self-replicating RNA molecules have come into existence on the early Earth? Let's return to our primordial soup, teeming with individual ribonucleotides, the building blocks of RNA, which we explored how they might have formed in previous discussions. In that ancient environment, where conditions allowed for the polymerization of these nucleotides into longer RNA strands on mineral surfaces or through cycles of wetting and drying in tidal pools, the stage was set. Now, imagine that among these randomly formed RNA strands, a few possessed a peculiar property. They could act as a template for the assembly of another strand, or even better, catalyze the formation of the bonds that link individual nucleotides together. This process is called template-directed synthesis. An existing RNA strand, perhaps a few dozen nucleotides long, would serve as a guide. Imagine this RNA strand as a long, flexible ribbon with its bases, adenine, uracil, guanine, and cytosine, exposed along one edge. Free-floating complementary nucleotides, present in the surrounding primordial soup, would then diffuse and align themselves along this template. Adenine would specifically recognize and weakly bind to uracil through hydrogen bonds, much like tiny molecular magnets finding their perfect partners. Similarly, guanine would pair with cytosine. This precise pairing, known as Watson-Crick base pairing, is the fundamental mechanism by which genetic information is copied in all life forms, even today. Once aligned, these individual nucleotides need to be chemically linked together to form a new, growing strand. This is the crucial polymerization step. In the RNA world, it's hypothesized that this linkage could have been catalyzed by the template RNA itself, or by another nearby RNA molecule acting as a ribozyme. Perhaps the specific three-dimensional folds of the template created a microenvironment that brought the reactive ends of the aligned nucleotides close enough and oriented them correctly for the phosphodiester bonds to form spontaneously or with minimal energy input. Another possibility is that the mineral surfaces we discussed in the previous chapter, like those of certain clays, such as montmorillonite, continue to play a role, providing a scaffolding and catalytic assistance for this crucial bond formation, concentrating the components and facilitating the necessary chemical reactions. The result of this process would be a new RNA strand, a negative copy that is complementary to the original template. But for true self-replication, we need to get back to an identical copy. This newly formed complementary strand could then detach and itself serve as a template, guiding the synthesis of yet another strand. This second round of template-directed synthesis would then produce a positive copy, identical in sequence to the very first original RNA molecule. This cyclical process, from original to negative copy, and then back to an original, completes the replication cycle. It's like making a photographic negative and then printing a positive from it. Each successful cycle would, ideally, double the number of these specific RNA molecules, allowing them to proliferate in their environment. However, this wasn't necessarily a perfect process. The early Earth was a dynamic and often chaotic place, and chemical reactions were not as precise as those orchestrated by modern enzymes. Errors would inevitably occur during replication. A wrong nucleotide might occasionally be incorporated, or a bond might form incorrectly. These mistakes, though seemingly detrimental, were in fact the very raw material for evolution. Each error introduced a slight variation in the newly formed RNA strands. Think of it like a scribe copying an ancient manuscript. Occasionally, a letter or word is miscopied. Most of these errors might make the text nonsensical, but once in a great while, a slight alteration might accidentally improve clarity or introduce a new, useful idea. In the RNA world, these misprints could lead to new RNA molecules with slightly different shapes, perhaps making them more stable, more efficient at replication, or even granting them entirely new catalytic abilities. This inherent imperfection, coupled with the potential for beneficial change, laid the groundwork for evolution by natural selection. Once self-replicating RNA molecules emerged, even in a primitive form, the stage was set for a rudimentary kind of natural selection. Imagine a pool filled with countless different RNA sequences, each a unique string of A's, U's, G's, and C's. Some of these sequences might be utterly useless, incapable of folding into any meaningful catalytic shape, or too unstable to persist. Others, however, might possess properties that gave them an edge. Perhaps one RNA molecule, let's call it replicous RNA, was particularly good at attracting free nucleotides and efficiently linking them into new strands, thus speeding up its own reproduction. Another, stabilizer RNA, might have folded into a structure that protected itself from degradation by harsh environmental factors, allowing it to survive longer. Yet another, resource finder RNA, might have been able to bind to and concentrate rare but essential chemical components, ensuring its access to raw materials. In this molecular free-for-all, the RNA sequences that could replicate faster, survive longer, or catalyze reactions beneficial to their own proliferation, would inevitably become more abundant. They would outcompete their less efficient counterparts for the limited supply of raw materials and space. This isn't evolution in the sense of complex organisms developing limbs or wings, but it is evolution at its most fundamental level: variation, selection, and differential reproduction. Over vast stretches of time, perhaps millions of years, these simple RNA replicators would have undergone a process of refinement, slowly evolving more efficient catalytic activities and more stable structures. They would have formed quasi-species, populations of related RNA molecules centered around a dominant, highly efficient sequence, but always surrounded by a cloud of slightly different, mutated variants. This constant variation allowed for continuous adaptation and improvement, driving the system towards greater complexity and efficiency. Could these early RNA molecules also cooperate? It's a fascinating thought, and scientific models suggest it's highly plausible. Imagine different RNA strands, each specializing in a particular task. One might be a highly efficient replicase, another a ligase that joins smaller RNA fragments, and yet another a synthetase that helps create more nucleotides from simpler precursors. If these different RNA types could somehow associate, perhaps within a small, localized region like a pore in a rock or a tiny lipid vesicle, they could form a rudimentary community where their combined functions led to a more robust and efficient overall replication system. This kind of mutual benefit could accelerate the emergence of even more complex, multifunctional RNA systems, setting the stage for the next great leap in life's origin. The RNA world hypothesis offers a compelling solution to the chicken or egg problem, providing a single molecular system that could perform both informational and catalytic roles, thereby kickstarting the process of evolution. But it also represents a transitional phase. Life as we know it today relies heavily on DNA for stable genetic storage and on proteins for their incredible catalytic versatility. So how did the RNA world give way to the DNA protein world? This transition was likely a gradual process, driven by the profound evolutionary advantages offered by these newer molecules. DNA, with its deoxyribose sugar and robust double-stranded structure, is far more chemically stable than RNA. This stability makes it an ideal molecule for long-term genetic archiving, protecting precious hereditary information from degradation and mutation over countless generations. Imagine if the blueprints for a house were written on highly reactive paper that crumbled easily. Eventually, you'd want to transfer those plans to something more durable and permanent. Early RNA systems might have evolved ribozymes capable of synthesizing DNA from RNA templates, a process similar to reverse transcription seen in some viruses today. Once DNA could be reliably synthesized and replicated, it would naturally take over the role of primary genetic storage due to its superior stability and fidelity. Similarly, proteins offered a much richer palette for catalysis. While RNA is versatile, its chemical repertoire is limited by its 4 nucleotide bases. Proteins, however, are built from 20 different amino acids, each with unique chemical properties and side chains. This diversity allows proteins to fold into an almost infinite variety of precise 3-dimensional structures, enabling them to catalyze reactions with far greater efficiency, specificity, and speed than most ribozymes. How might RNA have facilitated the emergence of proteins? The answer lies in the very heart of modern protein synthesis. The ribosome. The ribosome, the molecular machine responsible for translating genetic information into proteins, is itself a ribozyme, composed largely of ribosomal RNA. It is the ribosomal RNA, not protein, that catalyzes the crucial formation of peptide bonds between amino acids. This strongly suggests that RNA was at the forefront of early protein synthesis, perhaps initially binding to and joining amino acids, gradually evolving into the complex ribosomal machinery we observe today. So the RNA world wasn't a dead end, but a crucial stepping stone. It provided the evolutionary bridge, allowing for the development of both the stable genetic repository of DNA and the highly efficient enzymatic machinery of proteins. RNA, the original molecular jack-of-all-trades, eventually delegated its primary roles, information storage to DNA and catalytic function to proteins, while retaining essential intermediary and regulatory roles in modern cells. It became the wise elder, orchestrating the fundamental processes of life from behind the scenes, a testament to its foundational importance. Despite its elegant explanatory power, the RNA world hypothesis is not without its ongoing puzzles and active areas of research. One of the primary challenges is understanding how the specific building blocks of RNA, the ribonucleotides, could have formed under plausible early Earth conditions. While the formation of nucleobases, A, U, G, C, and sugars, ribose, separately, has been demonstrated in laboratory experiments. For instance, the Formose reaction can produce a variety of sugars, and simple precursors can yield nucleobases. The spontaneous assembly of a complete ribonucleotide, consisting of a base, a ribose sugar, and a phosphate group, in a single, efficient, and selectively favored pathway, remains a complex chemical hurdle. The phosphorylation step, adding the phosphate group, is particularly challenging in a watery environment without specific enzymes. Furthermore, the ribose sugar itself can exist in many forms, and life exclusively uses D-ribose. How this specific chirality was selected and concentrated remains an active area of investigation. Was it a chance event, or was there an underlying chemical bias? These difficulties have led some scientists to propose that a pre-RNA world existed, where an even simpler genetic polymer might have come first. Imagine a world where the first genetic material wasn't RNA, but a molecule that was chemically easier to synthesize under early Earth conditions. Candidates include PNA, peptide nucleic acid, which has a peptide-like backbone instead of a sugar phosphate one, or TNA, threose nucleic acid, which uses a 4-carbon sugar called threose instead of ribose. These simpler polymers might have been easier to synthesize prebiotically and could have served as initial templates for genetic information, later giving way to RNA as a more robust and versatile system. This stepping stone idea suggests that RNA itself might not have been the very first genetic molecule, but rather a significant evolutionary improvement that paved the way for DNA and proteins. Another key debate centers on the exact environmental conditions that would have best supported the emergence of self-replicating RNA. Were they the shallow, fluctuating tidal pools, where cycles of wetting and drying could concentrate molecules and drive polymerization, providing the energy for bond formation? Or were they the deep-sea hydrothermal vents, particularly the alkaline ones, offering continuous chemical energy, mineral surfaces, and protection from harsh surface radiation impacts? Perhaps different stages of this complex process occurred in different environments. The initial formation of nucleotides might have favored one setting, while their polymerization and the emergence of self-replication might have thrived in another. The early Earth was a mosaic of diverse environments, and it's plausible that life's origin story involves a grand tour of these varied landscapes, each contributing a crucial piece to the puzzle. Scientists around the world continue to probe these questions, using sophisticated laboratory experiments to recreate early Earth conditions and test various chemical pathways. The field of synthetic biology even attempts to build artificial self-replicating systems from scratch, offering tantalizing insights into the minimum requirements for life. These experiments are not just theoretical exercises. They are practical attempts to observe, in real time, how inanimate matter can begin to exhibit lifelike properties, how the fundamental laws of chemistry can give rise to the extraordinary phenomenon of self-organization and replication. The study of the RNA world, while seemingly abstract, has profound implications beyond just understanding our ancient past. It informs our search for life beyond Earth, suggesting that any extraterrestrial life might also have gone through a similar RNA-like phase. If life could arise from self-replicating polymers here, it might arise elsewhere under similar conditions, wherever the necessary chemical ingredients and energy sources are present. Furthermore, the knowledge gained from studying ribozymes and early genetic systems has led to remarkable technological spin-offs in medicine and biotechnology. For instance, Modified RNA molecules are now being developed as diagnostic tools, therapeutic agents, and even vaccines, demonstrating the enduring versatility of this ancient molecule. The very recent success of mRNA vaccines during the global pandemic highlights RNA's central role not just in the origin of life, but in its continuing evolution and our battle against disease. In essence, the RNA world hypothesis provides a powerful and elegant framework for understanding how the first glimmers of life might have ignited on our planet. It suggests a time when RNA, a molecule of surprising capabilities, bridged the vast chasm between non-living chemistry and the intricate biological systems we see today. It was a molecular crucible where information met function, where random chemical reactions began to organize into purposeful processes, and where the first seeds of evolution were sown. While many details of this ancient world remain shrouded in the mists of deep time, the ongoing quest to unravel the RNA world continues to push the boundaries of our understanding, revealing the remarkable ingenuity inherent in the universe's chemical possibilities. It reminds us that life is not a miraculous exception, but a probable outcome of physics and chemistry, given the right conditions and enough time. The journey from simple molecules to the first self-replicating entities was long and intricate, but the RNA world offers us a compelling glimpse into one of its most critical chapters. What happened next, as these early self-replicating systems began to organize themselves within protective boundaries, is the next crucial step in life's grand narrative. Imagine, for a moment, the vast, restless expanse of the early Earth's oceans, perhaps shimmering under a hazy, unfamiliar sky. Within this primordial soup, we've seen how simple ingredients could transform into complex polymers, like the fascinating RNA molecules, capable of carrying information and even catalyzing their own replication. These early self-replicators, the heart of the RNA world, were delicate, yet held the potential for life. But how could these fragile sparks of self-organization survive, let alone thrive, in such an immense and often turbulent environment? How could they concentrate the necessary ingredients to continue their intricate chemical dance when the surrounding waters constantly threatened to dilute and disperse them? This is where an incredibly simple yet profoundly revolutionary development took hold: the emergence of boundaries. The challenge was profound. Picture a single RNA molecule, perhaps a few hundred nucleotides long, capable of making copies of itself. For it to do so efficiently, it needs a steady supply of new nucleotides and other chemical helpers. In an open ocean, these essential components would be scattered, making encounters rare and slow. It would be like trying to bake a cake by throwing flour, eggs, and sugar into a vast swimming pool and hoping they find each other and combine. Life as we know it requires a contained space, a private workshop where chemical reactions can proceed efficiently, shielded from external interference. This need for a distinct internal environment, separate from the chaos outside, led to one of the most pivotal steps in life's origin, the birth of the protocell. The answer, surprisingly, lay in unassuming molecules known as lipids. You might recognize lipids as the fats and oils crucial to our own biology, forming cell membranes and storing energy. But on the early Earth, these simple fatty molecules possessed a remarkable, inherent property. Unlike many other organic compounds, lipids are amphiphilic. This means they have a dual nature. One part of the molecule, called the head, is hydrophilic, or water-loving, readily interacting with water. The other part, the tail, is hydrophobic, or water-fearing, actively repelling water. Imagine a tiny chemical with one end attracted to water and the other end trying to escape it. What would happen if you put a collection of these molecules into water? When confronted with water, these lipids don't simply dissolve. Instead, they spontaneously organize themselves in a truly elegant dance, driven by the fundamental laws of thermodynamics. The water-fearing tails try to escape the aqueous environment, while the water-loving heads happily interact with it. This leads to several predictable arrangements. Sometimes they form spherical clusters called micelles, where all the hydrophobic tails huddle together in the center, shielded from water, with the hydrophilic heads forming the outer surface. But a more profound structure emerges when the lipid tails are long enough and the concentration is just right. They form a bilayer. A lipid bilayer is essentially a double layer of these molecules. The hydrophobic tails point inward, meeting each other in the middle, creating a water-free core. The hydrophilic heads face outward, interacting with the water on both sides of this double layer. This structure is incredibly stable and forms the fundamental basis of all biological membranes today. Now, imagine this flat sheet of lipid bilayer, perhaps forming at the interface between water and air, or on the surface of a mineral. What happens if this sheet encounters turbulence, or simply grows large enough? Remarkably, these lipid bilayers have an inherent tendency to curl up and seal themselves into hollow spheres. These tiny bubbles, known as vesicles, are the earliest, most rudimentary form of a cell-like compartment. They are the protocells. Within their enclosed space, they can trap a small volume of the surrounding water, along with any molecules, like our precious self-replicating RNA, that happen to be present. This spontaneous self-assembly is not some complex biological process. It's a fundamental physical phenomenon driven by the simple interaction of lipids with water. It's a testament to how elegant solutions can arise from basic chemical principles. But where did these crucial lipids come from on the early Earth? The same processes that forged amino acids and nucleotides could have also produced fatty acids. Hydrothermal vents, with their energy-rich chemistry, could have synthesized them. The Miller-Urey type experiments, simulating early Earth conditions, also produce a variety of organic molecules, some of which could serve as precursors to lipids. Furthermore, meteorites and comets, which constantly bombarded the early Earth, have been found to contain a diverse array of organic compounds, including amphiphilic molecules that could spontaneously form vesicles, so the raw ingredients for these crucial boundaries were likely abundant and diverse. The conditions for vesicle formation would have been varied across the early Earth. Shallow tidal pools, subjected to cycles of wetting and drying, could have concentrated lipid molecules, encouraging their assembly. As water evaporated, the lipids would become more crowded, pushing them to organize. When the tides returned or rain fell, these concentrated lipids could then spontaneously form vesicles. Imagine the gentle lapping of waves against a primeval shore, or the rhythmic ebb and flow of a tide, providing the perfect agitation for these molecular self-assemblies. Deep-sea hydrothermal vents, too, could have been fertile grounds. The constant flow of fluids, gradients in temperature and pH, and the presence of mineral surfaces could have facilitated both the synthesis and the encapsulation of early life's components. The significance of this enclosure cannot be overstated. First and foremost, a protocell provided a means of concentration. Instead of valuable RNA molecules and their building blocks diffusing away into the vast ocean, they were now contained within a small, defined volume. This dramatically increased the likelihood of beneficial chemical reactions occurring. Imagine trying to find a specific person in a stadium versus finding them in a small room. The difference in reaction rates would have been immense, providing a significant advantage for any enclosed system. Secondly, these lipid membranes offered protection. The early Earth was not a gentle place. Intense ultraviolet radiation streamed down from the sun, unhindered by a protective ozone layer. Sudden changes in pH, temperature, or the presence of destructive metal ions could easily damage delicate RNA. A lipid membrane, however simple, acted as a shield, creating a more stable internal environment, a sanctuary where life's nascent chemistry could proceed without constant external assault. This internal milieu could maintain a specific chemical balance, distinct from the ever-changing outside world. Thirdly, and perhaps most crucially, the protocell allowed for the emergence of a unit of selection. In the RNA world, individual RNA molecules were competing, but once an RNA molecule and its ability to replicate was enclosed within a vesicle, the entire vesicle became the entity subject to natural selection. If the RNA inside a particular protocell replicated more efficiently, perhaps due to a beneficial mutation, that protocell would grow and eventually divide, passing on its successful internal chemistry and its membrane components to its descendants. This was the dawn of truly cellular evolution. It shifted the focus from individual molecules to integrated systems. But how did these simple protocells grow and divide? Unlike modern cells with their intricate machinery, early protocells would have relied on much simpler mechanisms. They could have grown by incorporating more lipid molecules from their environment, like a soap bubble expanding as more soap film is added. As they grew larger, physical forces, such as shear stress from currents, or the simple instability of a large spherical membrane, could have caused them to pinch off and divide into smaller daughter vesicles. Imagine a large blob of oil separating into smaller droplets when stirred. This rudimentary division, combined with the replication of internal RNA, meant that a successful protocell could propagate itself, albeit imperfectly. This brings us to a critical challenge and an ongoing area of scientific debate. How did the internal chemistry of the protocell interact with its external environment? Early lipid membranes were likely quite permeable, allowing small molecules like water, gases, and simple ions to pass through. This was essential for taking in nutrients and releasing waste products. However, too much permeability would defeat the purpose of enclosure. Modern cells have sophisticated protein channels and pumps to selectively transport molecules. Protocells had none of this. How did they achieve a balance between being leaky enough to exchange vital materials, yet robust enough to maintain a distinct internal composition? This permeability paradox is a fascinating puzzle scientists are actively exploring. One hypothesis suggests that the earliest membranes might have incorporated other molecules, such as short peptides, or even RNA fragments, that could act as primitive pores or channels, allowing selective passage of specific molecules. Another idea points to the role of certain ions, like magnesium, which can stabilize membranes and influence their permeability. The environment itself could also have played a role. For example, in environments with fluctuating salinity, membranes might swell and shrink, facilitating the uptake and release of molecules. Scientists today are actively working to recreate protocells in the laboratory by mixing plausible prebiotic lipids, sometimes with RNA or other polymers. They can observe the spontaneous formation of vesicles. These experiments show that these early compartments are not just theoretical constructs, but are experimentally verifiable phenomena. Researchers can even demonstrate how these artificial protocells can encapsulate genetic material, grow, and divide, mimicking the very first steps of cellular life. These synthetic protocells are helping us understand the delicate interplay between membrane formation, internal chemistry, and the beginnings of evolution. The emergence of the protocell marks a profound transition. It's the moment when chemistry, driven by the inherent properties of matter, began to organize itself into something resembling life. It was the crucial step where a collection of self-replicating molecules gained a physical identity, a boundary that defined self from not self. This simple enclosure elevated a diffuse chemical system into an autonomous entity, capable of maintaining its integrity and passing on its characteristics. It blurred the line between the inanimate and the animate, setting the stage for the true dawn of metabolism and the complex, self-sustaining systems we now call living organisms. Imagine a tiny bubble adrift in a vast ancient ocean. Inside, a fragile dance of molecules copying themselves, a whisper of life. Yet, what if those molecules ran out of raw materials, the very building blocks they needed to replicate? What if they couldn't mend themselves when damaged, or respond to the subtle shifts in their environment? Such a system, however groundbreaking, would be fleeting, a mere accident of chemistry, destined to dissolve back into the primordial soup. For life to truly take hold, for it to persist and evolve, something more profound, something truly revolutionary, had to emerge. The ability to make its own way. This was the dawn of metabolism and autonomy, the pivotal moment when a simple protocell, once a passive recipient of its surroundings, began to actively manage its own existence. It stopped simply absorbing what the ocean offered and started transforming it, harnessing energy and building its own complex components. This transition was not a sudden spark, but a gradual, intricate dance of chemical reactions, slowly weaving together into self-sustaining networks. It marked the blurring of the line between the non-living and the living, a profound step in the grand narrative of our origins. For billions of years before this point, the raw materials for life had been abundant. Amino acids, the building blocks of proteins and nucleotides, the units of RNA, were scattered throughout the early Earth, perhaps delivered by meteorites or forged in violent volcanic eruptions or deep-sea hydrothermal vents. These molecules accumulated in shallow pools or within the protective confines of clay minerals. We've seen how these simple molecules could polymerize into longer chains, forming early proteins and rudimentary RNA strands, and how fatty lipid molecules could spontaneously assemble into protective membranes, creating the first protocells. These early protocells were like fragile, leaky bags, capable of enclosing a few self-replicating RNA molecules. They might have grown by absorbing more lipids and molecules from their environment, and perhaps even divided when they grew too large, like a soap bubble stretching and splitting. But they were fundamentally dependent, passive vessels at the mercy of their environment, waiting for the right ingredients to diffuse in. The great challenge was energy. Chemical reactions require energy, and for a system to be self-sustaining, it needs to generate that energy internally, rather than relying on external random bursts. Modern life uses a complex molecule called adenosine triphosphate, or ATP, as its universal energy currency, but ATP itself is complex and would have been scarce on early Earth. So how did these nascent protocells begin to power themselves? The answer likely lies in simpler chemical gradients and redox reactions, where electrons are transferred from one molecule to another, releasing energy in the process. Consider the deep-sea alkaline hydrothermal vents, often called lost city vents. These towering, porous mineral structures, formed from reactions between seawater and the Earth's mantle, continuously release warm, alkaline fluids rich in hydrogen, methane, and sulfide. The surrounding ocean, in contrast, is cooler and more acidic, rich in carbon dioxide. This difference in acidity, or pH, creates a natural proton gradient across the porous walls of the vent, much like a tiny battery. Imagine these tiny pores as natural compartments, precursors to protocells, where the continuous flow of chemicals could drive simple reactions. Protons, which are essentially hydrogen ions, would naturally flow from the more acidic ocean into the more alkaline vent fluid, and this flow itself could provide the energy to drive the synthesis of organic molecules from simpler inorganic compounds like carbon dioxide and hydrogen. Could these natural energy gradients have been harnessed by the first protocells? Scientists hypothesize that early protocells, perhaps forming within the pores of these very vents, or later interacting with similar chemical gradients, developed primitive ways to capture this flow. Instead of relying on a complex proton pump, perhaps simple metal ions embedded in their primitive membranes, or even just the inherent charge differences across the lipid bilayer, could have facilitated the movement of charged particles, subtly driving metabolic processes. This wasn't an efficient system by modern standards, but it was a beginning, a faint flicker of self-generated power. With this rudimentary energy harnessing ability, protocells could take the monumental step of producing their own building blocks. Instead of waiting for a random amino acid to float by and diffuse through their membrane, they began to synthesize them from simpler, more abundant precursors. Imagine a protocell absorbing carbon dioxide, hydrogen, and ammonia from its surroundings. Through a series of catalyzed reactions, perhaps initially by simple mineral catalysts trapped inside, or by early ribozymes, RNA molecules with catalytic activity, these simple inorganic compounds could be transformed. Carbon dioxide could be fixed, meaning incorporated into organic molecules, a process known as carbon fixation, a cornerstone of all life today. Hydrogen could act as a reducing agent, donating electrons to create more complex molecules. Nitrogen from ammonia could be incorporated into amino acids and nucleotides. This internal synthesis was a game changer. It meant the protocell was no longer entirely dependent on the fluctuating availability of pre-formed organic molecules in its external environment. It gained a degree of independence. It could, to a limited extent, create its own supply chain. Think of it like a small self-contained factory. Initially, this factory might only produce a few types of essential parts, but even that small capability offered an immense evolutionary advantage. A protocell that could make its own amino acids would not starve if external supplies dwindled. It could grow and replicate more consistently, outcompeting its purely passive counterparts. This move from passive absorption to active biosynthesis represents a profound shift in the very nature of these nascent life forms. As these metabolic pathways became more intricate, they started forming interconnected networks. The product of one reaction would become the reactant for the next, creating a cascade of transformations. These early metabolic cycles, though far simpler than the sophisticated Krebs cycle or glycolysis we see in modern cells, were the engines of growth and self-maintenance. For instance, a protocell might use harnessed energy to convert inorganic carbon into a simple sugar, then use that sugar as a carbon skeleton to build an amino acid, and finally use that amino acid to assemble a new protoprotein or a new ribozyme. Each step catalyzed by a specific ribozyme or mineral, subtly improved the protocell's efficiency and resilience. What did this mean for the protocell itself? It meant growth, repair, and more efficient replication. A protocell with a nascent metabolism could grow larger, not just by absorbing external lipids, but by synthesizing new ones, actively expanding its membrane. It could also repair itself. If a part of its fragile RNA replication machinery was damaged, or if its membrane was compromised, its internal metabolic factories could churn out replacement parts, patching up the damage and maintaining its integrity. This was not the sophisticated DNA repair mechanisms or protein chaperones of modern cells, but a simple chemical form of self-maintenance. Most importantly, metabolism fueled replication. Making copies of RNA strands and synthesizing new membrane components requires significant energy and building blocks. A protocell that could generate its own energy and produce its own nucleotides would be able to replicate its genetic material more consistently and accurately. It could produce more daughter protocells, each inheriting the improved metabolic capabilities of its parent. This created a powerful feedback loop. Better metabolism led to more efficient replication, which in turn led to more protocells with better metabolism. This was the engine of early natural selection, operating at a chemical level. This stage marks the acquisition of true autonomy. An autonomous system is one that actively manages its own existence, rather than being a passive object acted upon by external forces. The protocell, with its emerging metabolic networks, began to control its internal environment, maintaining a stable chemical balance even as the external world fluctuated. It could respond to changes, adapt, and make choices, however rudimentary. If a necessary nutrient became scarce, it might shift its metabolic pathways to synthesize it from alternative precursors. If energy was abundant, it might invest more in growth and replication. This was the birth of agency, the first whisper of a will to live and persist. The line between non-living chemistry and living biology became incredibly blurry at this point. Was a protocell capable of rudimentary carbon fixation and self-replication truly alive? It wasn't a complex multicellular organism, nor even a fully formed bacterial cell. It lacked the sophisticated DNA-based genetic system and the vast protein machinery we associate with all modern life. Yet, it exhibited the fundamental characteristics: self-organization, self-replication with heredity, and a rudimentary metabolism that allowed it to grow and maintain itself. It was a chemical system that had learned to perpetuate itself, to actively resist entropy, the natural tendency towards disorder. The journey from simple atoms to a self-sustaining protocell was a long and arduous one, taking hundreds of millions of years. From the initial formation of organic molecules in the primordial soup, to their polymerization into complex chains, to their enclosure within lipid membranes, each step built upon the last. The emergence of metabolism within these enclosed systems was the crowning achievement, transforming passive chemical aggregates into dynamic, self-managing entities. It was the moment when inanimate matter truly began to learn to live, setting the stage for the explosion of biological diversity that would follow. The Earth, once a barren rock, was now home to tiny, industrious chemical factories, busily transforming their world and laying the groundwork for everything that was yet to come. Imagine for a moment looking at a single leaf gently swaying in the breeze, or observing the intricate dance of a tiny insect. Every living thing, from the smallest bacterium to the largest whale, shares an astonishing secret, a deep, ancient connection that stretches back billions of years to a single, humble ancestor. How could all the vibrant, diverse life we see around us today, with all its astounding complexity, trace its lineage back to one solitary simple cell? This is the profound question we now turn to as we explore the last universal common ancestor, or Luca. Our journey through the origins of life has taken us from the fiery birth of Earth and the creation of simple organic molecules through the intricate dance of polymerization, the revolutionary self-replicating world of RNA, and the crucial enclosure within lipid membranes to form the first protocells. These protocells, as we've explored, began to develop rudimentary metabolisms, harnessing energy and synthesizing their own building blocks, slowly gaining a fragile autonomy. They were no longer just passive bags of chemicals, but nascent systems actively managing their own existence. This gradual transition, however, still leaves a significant gap between these early, diverse chemical systems and the highly organized, universally similar life forms that dominate our planet today. This is where Luca enters our story. Luca stands for the last universal common ancestor, and it represents a pivotal point in Earth's history. It was not necessarily the first life form to emerge on our planet. It is highly probable that many different protocells and early life forms arose independently, experimented with various biochemical strategies, and competed for resources in the primordial oceans. Some of these early experiments in life may have thrived for a time, only to vanish, leaving no descendants. But among these nascent biological entities, one lineage, the one that would eventually lead to Luca, gained a critical advantage. This particular lineage outcompeted all others, eventually becoming the sole progenitor of every living organism we know, effectively resetting the biological clock and establishing a universal blueprint for life. So what exactly was Luca? We cannot point to a fossil of Luca, nor can we find it living in some hidden corner of the Earth. Instead, Luca is a conceptual entity, a kind of biological ghost defined by the common characteristics shared by all life forms alive today. It was a single, simple cell, likely prokaryotic in nature, meaning it lacked a nucleus or other membrane-bound organelles. Imagine a tiny microscopic sac, perhaps a few micrometers across, enclosed by a simple lipid membrane, filled with a watery cytoplasm. Within this cytoplasm, it contained the essential machinery for life, a form of genetic material, likely DNA by this point, a system for reading that genetic material and synthesizing proteins, and a basic set of metabolic enzymes to capture energy and build cellular components. This humble cell, existing over 3.5 billion years ago, was the ultimate progenitor, the singular point of divergence for all bacteria, archaea, and eukaryotes, the three great domains of life that now populate our world. How do scientists infer the existence and characteristics of something that lived so long ago, leaving no direct fossil evidence? The compelling evidence for Luca lies in the striking universality of fundamental biological processes and structures across all known life. If life had arisen multiple times independently, or if Luca were merely one of many coexisting ancestral forms, we would expect to see much greater diversity in the basic molecular machinery of different organisms. Instead, what we find is a profound unity. Perhaps the most astonishing piece of evidence is the Ersternange universal genetic code. Every living cell on Earth, from the smallest virus-infected bacterium to the cells in your own body, uses virtually the same language to translate genetic information stored in DNA, or RNA, into proteins. This code specifies that particular sequences of 3 nucleotides, called codons, correspond to specific amino acids, the building blocks of proteins. For example, the codon AUG almost universally codes for the amino acid methionine and also signals the start of protein synthesis. The codon UG consistently codes for tryptophan. There are 64 possible 3-letter combinations, coding for 20 common amino acids and a few stop signals. The fact that this intricate, seemingly arbitrary code is shared by virtually all life is incredibly powerful. Imagine if every book ever written, in every language, used the exact same alphabet, sentence structure, and vocabulary. It would strongly suggest a single origin point for all literature. Similarly, the universal genetic code points unequivocally to a common ancestor. While there are a handful of minor variations in the genetic code found in some mitochondria or certain bacteria, these are understood as later evolutionary tweaks, minor dialects of a fundamentally conserved language, rather than entirely different linguistic systems. This shared code is so fundamental that scientists routinely take a gene from one organism, say a human, insert it into a bacterium, and the bacterium will correctly read the genetic instructions and produce the human protein. This seamless transferability is a direct consequence of our shared ancestry with LearnTo. Beyond the genetic code, we find universality in shared metabolic pathways. All living cells require energy to sustain themselves and to synthesize their own components. The fundamental biochemical reactions that achieve this are remarkably conserved. Consider glycolysis, a metabolic pathway that breaks down glucose to release energy. This pathway, with its sequence of 10 enzyme-catalyzed reactions, is found in almost all organisms, from anaerobic bacteria living in oxygen-deprived environments to complex multicellular animals. Similarly, the Krebs cycle, also known as the citric acid cycle, and the electron transport chain, central to aerobic respiration, exhibit deep conservation across diverse life forms. The molecule adenosine triphosphate, or ATP, acts as the universal energy currency, powering nearly every cellular process. The pathways for synthesizing essential amino acids, nucleotides, and lipids also show remarkable commonality. These are not simple, obvious chemical reactions. They are complex, multi-step processes, and it is highly improbable that such intricate pathways would have evolved independently multiple times in precisely the same manner. Their widespread presence strongly suggests they were inherited from a common ancestor, LearnTo. Furthermore, all known life forms exhibit other deep similarities that point to LearnTo. All cells are enclosed by a lipid membrane, creating a distinct internal environment. All cells use ribosomes, complex molecular machines made of RNA and protein, to synthesize proteins. All cells utilize DNA as their primary genetic material, and the information flows from DNA to RNA to protein, a concept often called the central dogma of molecular biology. And most subtly, yet profoundly, all life on Earth uses only L-form amino acids to build proteins and deform sugars in nucleic acids. This molecular homochirality, the exclusive use of one mirror image form of molecules, is a powerful signature of a single origin. In non-living chemistry, both L and D forms are usually produced in equal amounts. The fact that life universally chose one form strongly suggests a single ancestral selection, preserved through billions of years of evolution. The existence of LearnTo represents the ultimate transformation, the point where the long, slow chemical evolution of abiogenesis culminated in a truly biological entity, capable of self-sustaining growth, self-replication, and, crucially, evolution by natural selection. Imagine the bustling chemical landscape of early Earth, filled with a myriad of protocells, each a tiny, enclosed experiment in nascent life. Some might have been more efficient at capturing energy, others better at replicating their genetic material, still others more robust in harsh conditions. Through competition and differential survival, the lineage that would give rise to LearnTo outcompeted all others, perhaps because it had developed a particularly efficient metabolism, a more stable genetic material, or a more robust system for protein synthesis. This triumph of one lineage over all others marked the true dawn of biological evolution, where genetic information passed down from LearnTo began to diversify and adapt, eventually leading to the breathtaking biodiversity we observe today. What are the profound implications of this understanding of abiogenesis and LearnTo? First, it fundamentally reshapes our understanding of life itself. It suggests that life is not a miraculous, inexplicable phenomenon, but rather a natural outcome of physics and chemistry under certain conditions. The journey from stardust to a self-aware being like ourselves is a continuous, unbroken chain of natural processes. We are, quite literally, stardust that learned to organize itself, replicate, and eventually to think and question its own origins. This perspective, far from diminishing the wonder of life, amplifies it, showing us the incredible power of self-organization inherent in the universe. Second, the concept of abiogenesis and LearnTo has immense implications for astrobiology, the search for life beyond Earth. If life emerged on Earth through natural processes, then it stands to reason that similar processes could occur elsewhere in the cosmos, given the right conditions. The universe is vast, containing billions of galaxies, each with billions of stars. Many of these stars are likely orbited by planets in their habitable zones, regions where liquid water, essential for life as we know it, could exist. The discovery of extremophiles on Earth, organisms that thrive in conditions previously thought to be uninhabitable, such as deep-sea hydrothermal vents, acidic lakes, or even within nuclear reactors, further broadens our understanding of where life might persist. If life can arise from non-living matter and adapt to such extreme niches on Earth, perhaps the universe teems with it. This scientific quest drives missions like NASA's Perseverance rover on Mars, which actively searches for signs of ancient microbial life, or future missions to icy moons like Europa and Enceladus, which harbor vast subsurface oceans that might resemble Earth's primordial environments. However, despite the compelling evidence for LearnTo and the robust hypotheses for abiogenesis, many uncertainties and open questions remain. Science is an ongoing journey of discovery, not a collection of settled dogmas. For instance, the precise environmental conditions where LearnTo lived are still debated. Was it in the warm, shallow tidal pools, rich with organic molecules, or deep within the protected, chemically active environments of Decatur? Hydrothermal vents. While the evidence for LearnTo's existence is strong, its exact metabolic profile, whether it was a chemoautotroph, deriving energy from chemical reactions and building its own organic molecules from carbon dioxide, or a heterotroph, consuming pre-existing organic molecules, is still a topic of active research. Scientists are also striving to understand the precise sequence of events that led from the relatively simple protocells we discussed in the previous chapters to the more complex, universally shared characteristics of LearnTo. This protocell-to-LuCa gap is a fascinating area of study. How did the transition from an RNA-dominated world to one where DNA stores genetic information and proteins perform most catalytic functions fully complete itself? What were the evolutionary pressures that drove these fundamental changes? And how did the intricate machinery of DNA replication and repair, essential for maintaining genetic integrity, evolve? The origin of molecular homochirality, the exclusive use of L-amino acids and D sugars, also remains a significant puzzle. While it's a strong indicator of common ancestry, the initial mechanism by which this handedness was established in prebiotic chemistry is still not fully understood. Some theories involve mineral surfaces, circularly polarized light from nebulae, or even chance fluctuations that were then amplified. The scientific quest to fully understand life's ultimate origins continues with vigor. Laboratory experiments tirelessly work to recreate prebiotic conditions, synthesizing complex organic molecules and even constructing self-assembling protocells. Researchers are exploring the catalytic properties of various minerals, simulating early Earth atmospheres, and examining the potential roles of cosmic dust and meteorites in delivering the raw ingredients for life. Astrobiologists continue to analyze data from other planets and moons, searching for biosignatures, any evidence of past or present life. Computational biologists model the evolutionary pathways that could have led to LuCa, testing hypotheses about early metabolic networks and genetic systems. This journey into abiogenesis and the discovery of LuCa is not just an academic exercise. It enriches our understanding of ourselves and our place in the universe. It reminds us that we are part of an incredibly ancient lineage, connected to every living thing by invisible threads of DNA and shared biochemical pathways. It encourages us to look at life in all its forms, with renewed wonder and respect, recognizing the billions of years of trial and error, adaptation and triumph that led to its present diversity. From the first whisper of stardust forming complex organic molecules, to the self-replicating dance of RNA, the protective embrace of protocell membranes, and the eventual emergence of a singular ancestor, LuCa, the story of life's origin is one of profound transformation. It is a testament to the inherent creativity of the universe, demonstrating how, under the right conditions, inanimate matter can indeed learn to live. The questions that remain are not obstacles, but invitations. Invitations to continue exploring, experimenting, and expanding the boundaries of our knowledge, to truly grasp the magnificent story of how we came to be.